Good evening, everyone, and welcome to Midnight Knowledge. Tonight, we're going to learn about do parallel universes really exist? So, as you settle in, please take a moment to let us know where you're listening from, and feel free to subscribe. Now, as we begin, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. Before we really dive into tonight's topic, I need to ask, how many of you have ever made a decision and immediately wondered, what if I had chosen differently? Okay, so basically all of you. What a shocker. Well, congratulations. You've just experienced the fundamental human intuition that leads us to today's question. Do parallel universes exist? Now, I know what some of you are thinking. Professor, did you just assign us a Marvel movie for homework? I assure you, while the multiverse has certainly captured Hollywood's imagination, we're going to explore the actual science behind these concepts. And trust me, the real physics is far stranger than anything you've seen on screen. Today, we're going to journey through one of the most mind-bending questions in modern cosmology and quantum physics. We'll explore multiple scientific theories that suggest parallel universes might not only be possible but inevitable. We'll examine the evidence, or lack thereof, and we'll grapple with what it would mean for our understanding of reality if these theories are correct. What are parallel universes? Let's start with definitions. When physicists talk about parallel universes, they're not necessarily talking about the same thing. The term parallel universe is actually an umbrella that covers several distinct concepts, each with its own theoretical foundation. At its most basic level, a parallel universe is a hypothetical universe that exists alongside our own, possibly with different physical laws, different histories, or different outcomes to the same events. But this simple definition masks a rich tapestry of possibilities that emerge from our best theories of physics. The physicist Max Tegmark has proposed a useful classification system that divides parallel universes into 4 levels, each more exotic than the last. Think of it as a cosmic taxonomy of weirdness, if you will. Level I universes are simply regions of space beyond our observable universe. These aren't really parallel in the science fiction sense. They're just really, really far away. Level 2 universes arise from cosmic inflation theory and represent regions with different physical properties. Level 3 universes come from quantum mechanics and represent different quantum outcomes. And level 4 universes are the most speculative. They represent all mathematically possible universes. We'll explore each of these in detail, but first, let's establish why serious physicists even entertain these ideas. After all, if you can't see something, measure it, or interact with it, why should we care whether it exists? The quantum mechanical foundation. To understand parallel universes, we need to start with quantum mechanics, that wonderfully counterintuitive theory that describes the behavior of matter and energy at the smallest scales, and I do mean counterintuitive. As physicist Niels Bohr once said, anyone who is not shocked by quantum theory has not understood it. In quantum mechanics, particles don't have definite properties until they're measured. Instead, they exist in what we call superposition, a combination of all possible states simultaneously. The classic example is Schrödinger's cat, which exists in a superposition of alive and dead states until someone opens the box to check. Now, here's where it gets interesting for our discussion. What happens when we make that measurement? The traditional Copenhagen interpretation says the superposition collapses into one definite state. The cat becomes either alive or dead. But in 1957, Hugh Everett III proposed a radical alternative. What if the superposition doesn't collapse? What if instead, the universe splits into multiple branches, one for each possible outcome? In Everett's many worlds interpretation, every quantum measurement creates a branching of reality. There's a universe where the cat is alive, and a universe where the cat is dead. There's a universe where you turned left at that intersection this morning, and a universe where you turned right. Every quantum event, and there are countless billions happening every second, spawns new universes. This sounds absurd, I know. It certainly sounded absurd to most physicists when Everett first proposed it. But here's the thing. It solves several puzzles in quantum mechanics without introducing any new assumptions. It's what we call a minimal interpretation. It takes the mathematics of quantum mechanics at face value without adding anything extra. Let me give you a concrete example. Consider a photon approaching a half-silvered mirror, a piece of glass that reflects 50% of the light that hits it and transmits the other 50%. According to quantum mechanics, until we measure it, the photon is in a superposition of being both reflected and transmitted. In the Copenhagen interpretation, the measurement forces it to choose one path. In the many worlds interpretation, the universe splits. In one branch, the photon was reflected. In another, it was transmitted. Now multiply this by every quantum interaction happening everywhere in the universe at every moment. The number of parallel universes becomes literally astronomical. In fact, it becomes infinite, cosmic inflation, and level 2 multiverses. While quantum mechanics gives us one type of parallel universe, cosmology offers another. This brings us to cosmic inflation theory, which addresses some puzzles about the early universe and, as a bonus, naturally leads to the existence of parallel universes. In the 1980s, physicists like Alan Guth realized that the early universe must have undergone a period of extremely rapid expansion, faster than the speed of light. This inflation explains several observed features of our universe: why it's so uniform in temperature, why it's geometrically flat, and why we don't see certain exotic particles that early universe theories predicted. But here's the kicker: once inflation starts, it's very hard to stop everywhere at once. Think of it like popcorn kernels in a pot. They don't all pop simultaneously. Some pop sooner, others later. Similarly, inflation likely ended at different times in different regions of space. This leads to what cosmologist André Linde calls eternal inflation. While inflation ended in our region of space 13.8 billion years ago, allowing matter and energy to condense into galaxies and stars, and, eventually, students sitting in lecture halls, it continues in other regions. These inflating regions spawn pocket universes, regions where inflation has ended and normal physics takes over. Each pocket universe could have different physical constants, different particle physics, different numbers of dimensions. The strength of gravity might be different. The mass of the electron might vary. The fine structure constant that governs electromagnetic interactions could take on different values. Most of these pocket universes would be uninhabitable. Change the strength of the strong nuclear force by just a few percent, and atomic nuclei can't form. Tweak the cosmological constant too much, and space expands so rapidly that galaxies never form, or conversely, the universe collapses before stars can ignite. This raises an interesting point known as the anthropic principle. We observe the physical constants we do because we exist to observe them. In a multiverse of infinite possibilities, it's inevitable that some universes will have just the right conditions for complexity, chemistry, and consciousness to emerge. We find ourselves in such a universe not because it's special, but because we couldn't exist in the others to wonder about it. The observable universe boundary. Now, let's dial back the exoticism a bit and consider level I multiverses, what Tegmark calls the simplest type of parallel universe. These aren't really parallel in the dramatic sense. They're just regions of space that are too far away for us to see. Our observable universe has a finite size because light has had only a finite time to reach us since the Big Bang. We can see light that has been traveling for 13.8 billion years, but due to the expansion of space, the most distant objects we can observe are now about 46 billion light-years away. This defines what we call the observable universe. But there's no reason to think that space stops at this boundary. It's like being on a ship in the middle of the ocean. You can see out to the horizon, but the ocean continues beyond what you can see. Similarly, the universe almost certainly continues beyond our observable horizon. If the universe is infinite and homogeneous, and our best observations suggest it might be, then every possible arrangement of matter that's allowed by physics exists somewhere. There would be regions identical to our observable universe, regions that are similar but with small differences, and regions that are completely different. In fact, if space is truly infinite and matter is distributed roughly uniformly, then the laws of probability guarantee that there are exact copies of you sitting in identical lecture halls, listening to identical lectures about parallel universes. There are also versions where you wore a different shirt today, versions where you chose a different major, and versions where you never existed at all. The distance to your nearest identical copy would be unimaginably vast, roughly 10 to the power of 10 to the 28th meters away, a number so large that writing it out would require more digits than there are atoms in the observable universe. But in an infinite universe, infinite distance is still just a finite address. String theory and extra dimensions. Our journey into parallel universes wouldn't be complete without discussing string theory, the ambitious attempt to unify all of physics into a single mathematical framework. String theory suggests that the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings of energy. One of the most striking predictions of string theory is that space has more than the 3 dimensions we experience. Depending on which version of the theory you consider, there could be as many as 10 or 11 dimensions of space. The extra dimensions are compactified, curled up so small that we don't notice them in our everyday experience. But here's where it gets interesting for our discussion. There are many ways to compactify these extra dimensions. Each different way of curling up the extra dimensions gives rise to a universe with different physical properties. The number of possibilities is enormous. Some estimates suggest 10 to the 500th different types of universes are possible. This landscape of possible universes provides another mechanism for generating parallel worlds. If cosmic inflation operates in this higher dimensional space, it could populate different regions with different types of compactification, creating a vast ensemble of universes with different physics. In some regions of this landscape, the strong nuclear force might be much weaker, making atomic nuclei unstable. In others, electromagnetism might be stronger, preventing the formation of large atoms. Most of these universes would be sterile, devoid of the rich chemistry necessary for life. But in the vast landscape of possibilities, some would hit the sweet spot that allows for complexity and consciousness. The mathematics of infinity. Let's take a moment to grapple with what infinity really means in the context of parallel universes, because our intuitions about infinity can lead us astray. When mathematicians talk about infinity, they're not just talking about a really big number. Infinity is a concept that transcends ordinary arithmetic, and when we combine infinity with probability theory, we get some deeply counterintuitive results. Consider this thought experiment. Imagine flipping a coin an infinite number of times. What's the probability that you'll get heads at least once? It's not just likely, it's absolutely certain. In fact, you'll get any finite sequence of heads and tails an infinite number of times. This principle applies to parallel universes. If there are infinitely many regions of space, and if the laws of physics allow for a finite, even if very large, number of possible arrangements of matter in any given volume, then every possible arrangement will occur infinitely many times. This includes arrangements identical to our solar system, our planet, and even our brains with all their memories and experiences. From a purely mathematical standpoint, there are infinitely many copies of you, scattered throughout an infinite universe. But here's where philosophy creeps into physics. What does it mean for there to be multiple copies of you? Are they all equally real? If an identical copy of you in a distant universe makes a different decision than you do, are you both equally valid versions of the same person? These aren't just abstract philosophical puzzles. They have implications for how we think about identity, consciousness, and moral responsibility in a multiverse scenario. Quantum computing and parallel processing. Now, you might wonder, if parallel universes are purely theoretical, why should we care about them? Well, it turns out that quantum mechanics' parallel worlds might not be just philosophical curiosities. They might be computational resources we can actually harness. This brings us to quantum computing, one of the most exciting frontiers in technology. Quantum computers exploit the weird properties of quantum mechanics, including superposition and what Einstein called spooky action at a distance, to perform certain calculations exponentially faster than classical. Computers. When a quantum computer is running an algorithm, it's not just processing one computation at a time. According to the many worlds interpretation, it's simultaneously performing the computation in multiple parallel universes, then cleverly combining the results when the quantum states are measured. David Deutsch, one of the pioneers of quantum computing theory, argues that this is the most compelling evidence for the many worlds interpretation. When your quantum computer factors a large number using Shor's algorithm, where exactly is all that computational work being done? If the many worlds interpretation is correct, the answer is in parallel universes. Each quantum bit or qubit in the computer exists in superposition, representing both 0 and 1 simultaneously. An n-qubit quantum computer can therefore exist in 2 to the power of n different states at once. A modest 300-qubit quantum computer would be exploring more computational paths simultaneously than there are atoms in the observable universe. From this perspective, quantum computers aren't just machines. They're windows into the parallel structure of reality itself. The problem of evidence. Now comes the elephant in the room. If parallel universes exist, how could we ever know? This is perhaps the most challenging aspect of multiverse theories. By definition, if we could interact with or observe another universe, it wouldn't really be parallel to ours. It would just be another part of a larger universe. This creates what philosophers call the evidential problem of parallel universes. How can we have scientific theories about things that are, in principle, unobservable? Isn't this more like theology than physics? The response from multiverse proponents is subtle but important. They argue that we don't need to observe parallel universes directly to have evidence for them. We just need evidence for the theories that predict them as inevitable consequences. Consider an analogy. We've never directly observed the center of the Earth. It's buried under thousands of miles of rock and metal, completely inaccessible to direct observation. Yet we have excellent evidence for what's down there because our theories of planetary formation, seismology, and gravitational dynamics all converge on the same picture. Similarly, if our best theories of quantum mechanics, cosmology, and particle physics all independently point toward parallel universes as inevitable consequences, then we might have indirect evidence for their existence. But the analogy has limits. We can test our theories about Earth's interior by studying seismic waves, magnetic fields, and gravitational anomalies. The effects of Earth's core reach the surface where we can measure them. Parallel universes, by contrast, seem to leave no measurable trace in our universe. This leads to legitimate questions about whether multiverse theories are scientific in the traditional sense. The philosopher Karl Popper argued that for a theory to be scientific, it must make predictions that could, in principle, prove it wrong. Theories that can't be falsified aren't science, they're metaphysics. Some multiverse theories may fail this test. If parallel universes can never be observed or tested, even in principle, then perhaps belief in them is more like religious faith than scientific knowledge. Experimental hints and indirect evidence. However, the picture isn't entirely bleak for multiverse evidence. While we can't observe parallel universes directly, some theories suggest there might be indirect ways to detect their influence. In quantum mechanics, some interpretations predict subtle deviations from standard quantum predictions in certain experiments. These deviations would be incredibly tiny and difficult to measure, but they might be detectable with sufficiently precise instruments. In cosmology, some versions of eternal inflation theory predict that our universe might occasionally collide with neighboring pocket universes, leaving distinctive signatures in the cosmic microwave background radiation. Several research groups have claimed to find such signatures, though the results remain controversial and haven't been independently confirmed. String theory makes mathematical predictions that can be tested, even if the parallel universes it predicts cannot. If string theory is correct in its description of particle physics and cosmology, this would lend credence to its predictions about the multiverse landscape. There's also the anthropic evidence I mentioned earlier. The fact that our universe seems fine-tuned for the existence of complexity and life is puzzling if our universe is all there is. But it's exactly what we'd expect in a multiverse, where most universes are sterile and we necessarily find ourselves in one of the rare habitable ones. Philosophical implications. The existence of parallel universes would have profound implications for philosophy, ethics, and our understanding of human nature. Let's explore some of these implications. First, consider the question of personal identity. If there are multiple copies of you scattered across parallel universes, which one is the real you? Are they all equally real? Do you have any special relationship to the copy in this universe as opposed to the others? This connects to deep philosophical questions about what makes you, you. Is it your physical body, your memories, your consciousness, your continuity through time? In a multiverse scenario, identical copies would share all of these features, yet they would have separate, independent existence. Then there's the question of moral responsibility. If every possible choice you could make is actually made by some version of you in some universe, does this diminish your responsibility for your choices? After all, in the many worlds interpretation, when you choose to help someone in need, there's another universe where you choose to walk away. Are both choices equally real? Some philosophers argue that moral responsibility becomes meaningless in a multiverse. Others contend that your choices still matter because they determine which branch of reality you experience, even if other branches also exist. There's also the question of meaning and significance. If everything that can happen does happen somewhere in the multiverse, does this make our universe and our lives less special? Or does it make them more precious because our particular branch of reality is unique, even if it's one among infinitely many? These aren't just abstract philosophical puzzles. As our scientific understanding of reality evolves, these questions become more pressing. If physics is pointing us toward a multiverse, we need to grapple with what this means for human experience and values. The Fermi paradox and parallel universes. Here's an interesting application of multiverse thinking to one of the great puzzles in astronomy, the Fermi paradox. Enrico Fermi famously asked, "Where is everybody?" Given the vast number of stars in our galaxy, many with planetary systems, and the billions of years available for evolution, why haven't we encountered any evidence of alien civilizations? Various solutions have been proposed. Maybe life is rarer than we think. Maybe intelligence is a rare evolutionary development. Maybe advanced civilizations destroy themselves. Or maybe they're hiding from us. But the multiverse offers another perspective. If there are infinitely many parallel universes, then there are universes teeming with alien life and others that are completely sterile. Perhaps we find ourselves in a relatively empty universe, simply because empty universes vastly outnumber crowded ones, or because the specific physical constants in our universe make complex life extremely rare. Alternatively, if the many worlds interpretation is correct, there are branches of quantum reality where we have encountered alien life, branches where humanity never evolved, and branches where Earth itself never formed. We happen to experience the branch we're in, but all possibilities play out somewhere. This perspective doesn't solve the Fermi paradox so much as reframe it. Instead of asking why we don't see aliens, we might ask why we're experiencing the branch of reality where aliens are absent, when other branches might be full of galactic civilizations. Criticisms and skepticism. Not everyone in the physics community embraces parallel universes. Let me present some of the major criticisms, because scientific integrity requires us to consider opposing viewpoints. The most fundamental criticism is Occam's razor, the principle that we should prefer simpler explanations over more complex ones. Creating an infinite number of unobservable universes to explain our observations seems like the opposite of simplicity. Critics argue that invoking parallel universes is like solving one mystery by creating infinitely many larger mysteries. Nobel Prize winner Steven Weinberg has expressed skepticism about multiverse theories precisely on these grounds. He worries that if we can explain any observation by appealing to selection effects in a multiverse, then we lose the ability to make meaningful predictions about what we should observe. Another criticism comes from the measurement problem in quantum mechanics. The many worlds interpretation is supposed to solve this problem by eliminating wave function collapse, but critics argue that it just pushes the problem to a different level. How do we explain why we experience one particular branch of reality rather than others? What determines which branch corresponds to our conscious experience? Some physicists, like Roger Penrose, argue that consciousness plays a fundamental role in quantum measurement that the many worlds interpretation fails to address. If consciousness is what selects which quantum outcomes we experience, then the multiplication of unconscious universes doesn't solve the original problem. There's also what we might call the utility criticism. Even if parallel universes exist, what difference does it make to our lives or our science? We can only ever interact with our own universe, so the others are irrelevant to any practical concerns. Finally, there's the criticism from falsifiability. As I mentioned earlier, if multiverse theories can't be tested or potentially disproven, then they might not qualify as science in the traditional sense. Current research and future prospects. Despite these criticisms, research into parallel universes continues across multiple fronts. Let me give you a sense of what scientists are currently working on and where the field might be headed. In quantum mechanics, researchers are designing increasingly sophisticated tests of the different interpretations. Some focus on finding quantum effects that might distinguish between the many worlds interpretation and alternatives. Others explore the boundary between quantum and classical physics, looking for places where quantum superposition breaks down. The field of quantum computing is providing new laboratories for testing quantum mechanical principles. As quantum computers become more powerful, they might reveal new aspects of quantum reality that could shed light on the parallel universe question. In cosmology, the search for evidence of eternal inflation continues. The Planck satellite and other missions have mapped the cosmic microwave background with unprecedented precision, looking for signatures of collisions between pocket universes or other evidence of a larger multiverse. Future gravitational wave detectors might be sensitive enough to detect primordial gravitational waves from the inflationary epoch, which could provide evidence for eternal inflation theories. String theorists continue to explore the landscape of possible universes, trying to understand which types of universes are most likely to arise from string theory, and whether there are observable consequences that distinguish string theory from alternative approaches. There's also growing interest in the intersection of multiverse theory and artificial intelligence. Some researchers speculate that advanced AI systems might be better equipped than humans to explore the implications of living in a multiverse or even to simulate parallel universes computationally. The anthropic principle revisited. Let me return to the anthropic principle, because it's central to many multiverse arguments and deserves deeper exploration. The anthropic principle comes in two forms, weak and strong. The weak anthropic principle simply states that we observe the universe to be compatible with our existence, because if it weren't, we wouldn't be here to observe it. This is relatively uncontroversial. It's just a selection effect. The strong anthropic principle is more controversial. It suggests that the universe must have properties that allow observers to develop within it at some point in its history. This comes dangerously close to suggesting that the universe was designed for life, which makes many scientists uncomfortable. The multiverse provides a middle path. In a multiverse, most universes are uninhabitable, but the few that can support observers will necessarily be observed by the life forms they contain. We don't need to invoke design or purpose, just statistics. But this raises the question of probability. In an infinite multiverse, how do we calculate the probability that we should observe particular features of our universe? This leads to the measure problem in cosmology, the challenge of assigning meaningful probabilities to events in infinite sets. Different ways of counting universes in the multiverse give different predictions for what we should observe. Some approaches predict that we should observe a universe very different from the one we actually see. This is an active area of research, with implications for both cosmology and the foundations of probability theory. Life in a multiverse. Let's consider what it would mean for human life and civilization if parallel universes exist. This might seem like science fiction, but it's worth thinking through the implications seriously. If the many worlds interpretation is correct, then every quantum event in your body, every neural firing, every genetic mutation, every random molecular collision, creates branches in reality. Most of these branches would be nearly identical to each other, but some would be significantly different. There would be branches where you made different life choices, branches where you were never born, branches where humanity evolved differently or not at all. From your subjective perspective, you experience only one branch, but from a global perspective, all possibilities play out. This might seem to make individual choices less meaningful, but many philosophers argue the opposite. Your choices still determine which branch of reality you experience, which is the only branch that matters from your perspective. If cosmic inflation creates pocket universes with different physical laws, then there might be universes where evolution took completely different paths, where chemistry works differently, where the concept of life as we understand it doesn't apply. Some universes might have developed civilizations far more advanced than ours, with technologies we can barely imagine. Others might be stuck in pre-technological states, or might have destroyed themselves through warfare or environmental catastrophe. The humbling implication is that our universe, with all its galaxies and complexity, might be just one tiny bubble in an infinite foam of realities, most of which are utterly alien to our experience. The ultimate question. This brings us back to our original question. Do parallel universes exist? After everything we've discussed, I hope you can see that this isn't just a yes or no question. Depends on which theories prove correct, how we interpret quantum mechanics, whether cosmic inflation is eternal, and how we define existence itself. The honest answer is that we don't know. We have theories that predict parallel universes as inevitable consequences, but we haven't definitively proven these theories correct. We have indirect evidence and philosophical arguments, but no smoking gun. What we can say is that parallel universes are a serious possibility that emerges naturally from our best current theories of physics. They're not just science fiction fantasies, they're logical implications of mathematics that has proven remarkably successful at describing the natural world. Whether or not parallel universes exist, the question has already enriched our understanding of quantum mechanics, cosmology, and the nature of reality itself. It's forced us to think more carefully about the relationship between theory and observation, about the role of consciousness in physics, and about what we mean when we ask whether something is real. Conclusion. We've journeyed through quantum superposition and cosmic inflation, through string theory landscapes and anthropic selection effects. We've grappled with infinite multiplicities and unmeasurable realities. We've considered both the mathematical elegance and the philosophical puzzles that parallel universes present. The question of parallel universes sits at the intersection of our most fundamental theories of physics and our deepest questions about existence, consciousness, and meaning. Whether or not other universes exist beyond our cosmic horizon or in quantum parallel realities, the very possibility forces us to expand our conception of what reality might encompass. Perhaps the most important lesson is humility. The universe, or multiverse, might be far stranger and more magnificent than our everyday experience suggests. We might be part of something vastly larger than we can directly perceive, something that challenges our intuitions about identity, causation, and significance. Science often leads us to uncomfortable places, forcing us to abandon cherished assumptions about our place in the cosmos. Copernicus showed us that Earth isn't the center of the universe. Darwin showed us that humans aren't separate from the natural world. Quantum mechanics showed us that reality doesn't work the way our classical intuitions suggest. The possibility of parallel universes continues this tradition of cosmic humbling, suggesting that even our entire universe might not be unique or central to the larger structure of reality. But there's also something profoundly hopeful in this perspective. If parallel universes exist, then every moment of beauty, every act of kindness, every scientific discovery, and every work of art occurs not just once, but countless times across the multiverse. The universe, or universes, might be filled with versions of us and beings unlike us, all exploring the possibilities of existence. For now, we can only observe our single branch of reality, ask our questions, and follow the mathematics wherever it leads. Whether we live in a universe or a multiverse, the search for understanding remains the same. We're still left with the fundamental human task: to observe, to question, to theorize, and to wonder at the magnificent strangeness of existence itself. The question, do parallel universes exist, might not have a definitive answer yet, but asking it has already taught us something profound about the nature of reality and our place within it. And perhaps, in the end, that's the most important thing any scientific question can do. Not just provide answers, but expand our sense of what's possible. Thank you for joining me on this journey through the possible structure of reality. Okay, that's it for tonight. Until next time, every time you make a choice, remember, somewhere in the quantum foam or beyond the cosmic horizon, every other choice might be playing out as well. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you. Tonight we're going to embark on an electrifying journey, and I promise that's the only lightning pun I'll make in the first 5 minutes. What a shocker, right? Guess these jokes will really give you a jolt. Buckle up, because we're heading to a place where Mother Nature apparently forgot to install an off switch on her cosmic disco ball. Lake Maracaibo in Venezuela, home to the phenomenon known as Catatumbo lightning, or as locals call it, Relámpago del Catatumbo. Imagine, if you will, a place where lightning strikes the sky with such regularity that you could practically set your watch by it. A place where the phrase "lightning never strikes twice" is not just wrong, but laughably spectacularly wrong. We're talking about a natural phenomenon so consistent, so reliable, that ancient sailors used it as a lighthouse, and modern researchers use it as the world's most impressive natural laboratory for studying atmospheric electricity. Let's start with some numbers that will, quite literally, shock you. The Catatumbo lightning phenomenon occurs in the area where the Catatumbo River flows into Lake Maracaibo in northwestern Venezuela. This region experiences an absolutely mind-boggling amount of electrical activity that puts every other place on Earth to shame. We're talking about 250 lightning strikes per square kilometer per year. To put that in perspective, most places on Earth consider themselves lucky or unlucky, depending on your perspective, to see a few dozen lightning strikes per square kilometer annually. Lake Maracaibo laughs in the face of such modesty. This region experiences lightning on approximately 297 nights per year. That's more than 80% of all nights. If lightning were a Netflix show, Catatumbo would have watched every episode twice and be asking for a spin-off. During peak activity, which typically occurs between April and November, the area can experience up to 250 to 300 flashes per minute. Yes, you heard that correctly. Per minute, not per hour. At its absolute peak, we're looking at nearly 5 lightning strikes every single second. It's as if Zeus decided to throw the world's most intense rave and forgot to send out the last call announcement. The lightning typically begins about an hour after dusk and continues for approximately 10 hours per night during active periods. The storms generally rage between the coordinates 8 degrees 30, north 70, 1 degrees 0, west, and 9 degrees 45 north, 73 degrees 0 west, creating what researchers have dubbed the lightning capital of the world, a title that Lake Maracaibo wears with well-deserved pride. But here's what makes this phenomenon truly remarkable. It's not random. This isn't just a case of really bad luck with the weather. This is a systematic, predictable, and ongoing natural phenomenon that has been documented for over 500 years. When Spanish explorer Lope de Vega wrote about the continuous lightning that seems never to end, he wasn't exaggerating for dramatic effect. He was providing what we now recognize as one of the earliest scientific observations of this incredible natural phenomenon. To understand why Catatumbo lightning exists, we need to examine the unique geographical cocktail that makes this phenomenon possible. Lake Maracaibo sits in what meteorologists affectionately call a perfect storm of geographical features, and in this case, that's not a metaphor. Lake Maracaibo is South America's largest lake, covering approximately 13,210 square kilometers. But it's not just any lake, it's a brackish lagoon that opens to the north into the Caribbean Sea. This connection to the Caribbean is crucial because it allows warm, humid air masses to flow directly into the lake basin. Think of it as Mother Nature's own humidifier, except instead of making your skin feel nice, it creates the most spectacular lightning show on the planet. The lake is surrounded by mountains on three sides, the Andes Mountains to the south and west, and the Perija Mountains to the east. This creates what meteorologists call a topographic bowl, or natural amphitheater. During the day, the intense tropical sun heats the lake's surface, causing massive evaporation. This warm, moisture-laden air rises throughout the day, but here's where the geography becomes crucial. As the sun sets, the surrounding mountains begin to cool more rapidly than the lake's surface. Mountains always cool faster than water bodies, because rock and soil have lower heat capacity than water. This creates temperature differentials that drive wind patterns. Cool air from the mountains begins to flow down toward the warmer lake surface, creating what meteorologists call mountain breezes or katabatic winds. Now, imagine you're a parcel of warm, humid air that's been rising from the lake all day. Suddenly, you encounter these rivers of cool, dense air flowing down from the mountains. It's like a meteorological traffic jam, except instead of frustrated commuters, you get massive convective storms. The collision between these air masses creates the perfect conditions for thunderstorm development. But wait, there's more. The Catatumbo River itself plays a crucial role. As it flows into Lake Maracaibo, it brings additional moisture and creates localized areas of instability. The river delta is a maze of wetlands, swamps, and marshes that serve as additional moisture sources. During the day, these wetlands superheat and pump even more water vapor into the atmosphere. The combination of lake evaporation, wetland transpiration, mountain-valley wind systems, and the convergence zone created by the river delta creates what scientists call a mesoscale convective complex, a fancy term for the perfect recipe for continuous thunderstorms. Now that we understand the geographical stage, let's examine the atmospheric physics that creates this incredible show. Lightning formation requires three key ingredients: moisture, instability, and a lifting mechanism. Lake Maracaibo has all three in abundance, which is why it produces more lightning than anywhere else on Earth. First, let's talk about moisture. The process begins with evaporation from Lake Maracaibo's 13,210 square kilometer surface. On a typical day, millions of tons of water evaporate into the atmosphere. This creates what meteorologists call a boundary layer, a zone of extremely humid air extending from the surface up to several hundred meters in altitude. As this moisture-laden air heats up during the day, it becomes less dense than the surrounding air and begins to rise through convection. Under normal circumstances, this rising air would eventually reach an altitude where it cools enough to form clouds and perhaps produce a brief afternoon thundershower. But at Lake Maracaibo, the process is supercharged by the unique topography. The instability component comes from the dramatic temperature contrasts created by the geographical setting. During the day, the lake surface can reach temperatures of 30 to 35 degrees Celsius, 86 to 95 degrees Fahrenheit, while the air temperatures at mountain elevations, just a few dozen kilometers away, might be 15 to 20 degrees cooler. This creates enormous potential for convective overturning. Essentially, the atmosphere becomes a giant convection oven with the lake as the heating element. The lifting mechanism is provided by the mountain valley wind system. As evening approaches and the mountains cool, dense, cool air flows down the mountain slopes toward the warmer lake surface. This creates a convergence zone where different air masses collide. In meteorology, convergence zones are like atmospheric particle accelerators. They force air upward with tremendous energy. When warm, humid air is forced upward rapidly, It undergoes adiabatic cooling. It cools due to decreasing atmospheric pressure at higher altitudes. As the air cools, its capacity to hold moisture decreases, leading to condensation and cloud formation. But the process doesn't stop there. The latent heat released during condensation actually adds energy to the system, causing the air to rise even faster. This creates a positive feedback loop that can drive convective clouds to extraordinary heights, often exceeding 15 kilometers in altitude. These towering cumulonimbus clouds become the factories where lightning is manufactured. Inside these massive clouds, ice crystals and water droplets are carried up and down by powerful updrafts and downdrafts. The collision between ice particles creates electrical charge separation through a process called triboelectrification. Essentially, friction between ice particles creates static electricity on a massive scale. Typically, the upper portions of the cloud accumulate positive charge, while the lower portions accumulate negative charge. When the electrical potential difference becomes great enough, usually several million volts, nature finds a way to balance the books through lightning discharge. Not all lightning is created equal, and the Catatumbo phenomenon showcases the full spectrum of electrical discharge types. Understanding these different forms helps us appreciate the complexity and beauty of this natural phenomenon. The most common type observed at Catatumbo is intracloud lightning, also called sheet lightning. This occurs entirely within a single cloud and accounts for approximately 75% of all lightning activity in the region. These discharges illuminate the entire cloud from within, creating what locals poetically describe as illuminated cotton balls floating in the night sky. While intracloud lightning doesn't strike the ground, it's responsible for the characteristic glow that makes the Catatumbo phenomenon visible from hundreds of kilometers away. Cloud-to-ground lightning, the type most people picture when they think of lightning, occurs when the electrical discharge travels from the negatively charged base of a cloud to the positively charged ground surface. At Catatumbo, these strikes are particularly spectacular because they often occur over the lake's surface, creating dramatic reflections that double the visual impact. The high mineral content of Lake Maracaibo's brackish water makes it an excellent conductor, which may contribute to the frequency of water strikes. Cloud-to-cloud lightning occurs between separate storm cells and is particularly common at Catatumbo due to the tendency for multiple storm systems to develop simultaneously across the lake basin. These horizontal flashes can extend for dozens of kilometers, creating dramatic branching patterns across the sky. One of the most visually stunning types is positive lightning, which originates from the positively charged upper portions of clouds. While less common than negative lightning, positive strikes are significantly more powerful, often carrying currents 5 to 10 times stronger than typical negative strikes. At Catatumbo, positive lightning creates some of the most brilliant flashes, occasionally bright enough to read a newspaper by their light alone. The phenomenon also produces what researchers call superbolts, extraordinarily powerful lightning strikes that release energy equivalent to several billion joules. These rare events are so intense that they can be detected by satellites from space and often produce thunder that can be heard from over 25 kilometers away. Perhaps most intriguing are the upward lightning strikes that sometimes occur from the lake's surface or nearby elevated terrain. These rare discharges begin at ground level and propagate upward toward the clouds, typically occurring when the electric field strength at ground level becomes so intense that it initiates its own discharge channel. Recent research has also identified what scientists call lightning sprites, high-altitude electrical phenomena that occur above the main storm clouds. These ethereal, jellyfish-like discharges appear in the upper atmosphere between 50 and 90 kilometers above the Earth's surface and are triggered by particularly powerful cloud-to-ground strikes below. The Catatumbo lightning phenomenon has been known to humans for centuries, long before we understood the scientific principles behind it. Indigenous groups in the region, including the Wayu, Yukpa, and Bari peoples, developed rich mythological traditions around what they called the River of Fire. The The Berry people believed the lightning was created by millions of fireflies that gathered in tribute to the gods, while the Wayuu saw it as the spirits of their ancestors dancing in the sky. These weren't just pretty stories. They reflect sophisticated observations of the phenomenon's patterns and characteristics. Indigenous knowledge keepers understood that the lightning followed seasonal patterns, was more intense during certain months, and could be used to predict weather changes days in advance. When Spanish explorers arrived in the early 16th century, they quickly recognized the navigational value of what they called El Faro de Maracaibo, the lighthouse of Maracaibo. The consistent glow on the horizon served as a reliable beacon for ships navigating the Caribbean coast. Unlike artificial lighthouses, which could be extinguished or destroyed, the Catatumbo lightning provided a natural navigation aid that operated nearly every night of the year. Historical records from the colonial period describe how ship captains would deliberately time their voyages to take advantage of the lightning's illumination. The phenomenon was so reliable that it appeared on maritime charts as an official navigation aid. One 18th century Spanish naval manual specifically instructs captains to look for the eternal lightning when approaching the Venezuelan coast. The lightning also played an unexpected role in military history. During the South American Wars of Independence in the early 1800s, the phenomenon inadvertently influenced several naval battles. In 1823, a Spanish fleet attempting a surprise night attack on the port of Maracaibo was revealed by the lightning's illumination, allowing Republican forces under Admiral José Prudencio Padilla to prepare their defenses and ultimately win the Battle of Lake Maracaibo. The first serious scientific study of the phenomenon began in the late 19th century, when German naturalist Alexander von Humboldt included observations of the lightning in his comprehensive survey of South American natural phenomena. Humboldt was the first to propose that the lightning was caused by organic matter. Specifically, he theorized that methane gas rising from the lake's organic-rich sediments was somehow igniting to create the electrical displays. While Humboldt's methane theory was eventually disproven, his systematic approach to documenting the phenomenon established the foundation for modern scientific research. He meticulously recorded the lightning's seasonal variations, noted its correlation with local weather patterns, and produced the first maps showing the geographical extent of the electrical activity. The 20th century brought increasingly sophisticated scientific investigation. In the 1960s, Venezuelan meteorologist Melchor Centeno conducted the first systematic electrical measurements of the phenomenon, using primitive instruments to record voltage differentials and electromagnetic signatures. His work confirmed that the Catatumbo lightning was indeed a purely atmospheric electrical phenomenon, not related to ground-based gas emissions. The advent of satellite technology in the 1970s and 1980s revolutionized Catatumbo research. For the first time, scientists could observe the phenomenon from space, leading to startling discoveries about its true scale and intensity. NASA's Lightning Imaging Sensor, LIS, data revealed that the Catatumbo region produces more lightning per square kilometer than anywhere else on Earth, by a significant margin. Contemporary research on Catatumbo lightning employs some of the most sophisticated atmospheric monitoring technology available to science. The phenomenon serves as a natural laboratory where researchers can study atmospheric electricity under extreme conditions, leading to insights that benefit everything from weather prediction to aviation safety. NASA's Earth observation satellites continuously monitor the region using multiple sensor systems. The Lightning Imaging Sensor, LIS, and the Optical Transient Detector, OTD, provide real-time data on lightning frequency, intensity, and geographical distribution. This data reveals fascinating patterns. For instance, recent research published in the Journal of Geophysical Research shows that daily lightning patterns are directly linked to changes in deep storm activity, and seasonal variations correlate with monthly changes in the lake's average water temperature. Ground-based research stations around Lake Maracaibo employ networks of sophisticated instruments, including lightning detection arrays, atmospheric electric field monitors, radar systems, and weather stations. These instruments work together to create a comprehensive picture of the atmospheric conditions that generate and sustain the lightning activity. One particularly exciting development is the use of radio frequency analysis to study lightning characteristics. Each lightning strike produces a unique electromagnetic signature that can be analyzed to determine the discharge's power, duration, and type. This technique has revealed that Catatumbo lightning includes an unusually high percentage of extremely powerful discharges, what researchers call superbolts, compared to lightning in other regions. High-speed photography and video analysis have provided unprecedented insights into the structure and behavior of individual lightning strikes. Using cameras capable of recording at millions of frames per second, researchers have documented the step-by-step progression of electrical discharges, revealing complex branching patterns and multiple stroke events that occur too quickly for the human eye to perceive. Computer modeling and atmospheric simulation represent another frontier in Catatumbo research. Scientists use powerful supercomputers to create detailed simulations of the atmospheric conditions around Lake Maracaibo, testing different theories about what drives the phenomenon's exceptional intensity and consistency. These models incorporate factors including topography, lake temperature variations, wind patterns, humidity levels, and seasonal temperatures. By adjusting different variables in the simulation, researchers can test hypotheses about which factors are most critical for lightning formation and what might cause variations in activity levels. Recent modeling work has confirmed the critical importance of the lake's heat capacity in driving convective processes. The simulation shows that Lake Maracaibo acts as a massive thermal flywheel, storing solar energy during the day and releasing it gradually throughout the night. This sustained heat source maintains atmospheric instability long after sunset, providing the energy needed for continuous storm development. One of the most significant recent discoveries involves the role of aerosols, tiny particles suspended in the atmosphere, in lightning formation. Research indicates that dust, salt particles, and organic matter in the air above Lake Maracaibo may serve as nucleation sites for ice crystal formation within storm clouds. This process, called cloud seeding, may enhance the charge separation that ultimately produces lightning. The Catatumbo lightning phenomenon doesn't exist in isolation. It plays crucial roles in the regional ecosystem and has significant environmental implications that extend far beyond the immediate area around Lake Maracaibo. Lightning produces nitrogen oxides, NOx, through the extreme heat of electrical discharge, which breaks apart nitrogen molecules in the atmosphere and allows them to combine with oxygen. These compounds eventually fall to Earth as nitrates, serving as natural fertilizer for plants. At Catatumbo, where lightning activity is orders of magnitude higher than typical regions, this natural fertilization process is correspondingly intense. Scientists estimate that the Catatumbo lightning contributes approximately 1,000 to 2,000 tons of nitrogen compounds to the regional ecosystem annually. This natural fertilization helps explain the exceptional biodiversity of the wetlands around Lake Maracaibo. The region supports over 2,000 plant species, including many endemic varieties that exist nowhere else on Earth. The lightning also plays a role in atmospheric chemistry on a regional scale. The electrical discharges produce ozone in the lower atmosphere through photochemical reactions. While ground-level ozone is often considered a pollutant in urban areas, in the natural environment around Lake Maracaibo, it contributes to complex atmospheric chemistry that helps regulate local climate patterns. The intense electrical activity creates electromagnetic effects that influence local wildlife behavior. Research has documented changes in bird migration patterns during periods of intense lightning activity. Some species appear to avoid the area during peak electrical storms, while others seem adapted to navigate around the phenomenon. The lake's fish populations also show interesting adaptations to the electrical environment. Several species of electric fish found in Lake Maracaibo display enhanced electroreception abilities compared to their relatives in other bodies of water, possibly as an adaptation to the intense electrical environment. The phenomenon has significant implications for local agriculture. Farmers in the region have traditionally planned planting and harvesting schedules around the lightning seasons, taking advantage of the enhanced nitrogen deposition during periods of intense electrical activity. Traditional agricultural knowledge passed down through generations includes sophisticated understanding of how lightning patterns correlate with soil fertility and crop yields. Interestingly, the lightning activity shows correlation with larger weather patterns, including the El Niño Southern Oscillation, ENSO. During El Niño years, when Pacific Ocean temperatures are elevated, the Catatumbo lightning tends to be less intense, possibly due to altered atmospheric circulation patterns that disrupt the local conditions necessary for optimal storm formation. The Catatumbo lightning phenomenon has profoundly shaped the culture, economy, and daily life of the communities around Lake Maracaibo. For the approximately 7 million people who live in the region, about a quarter of Venezuela's total population, the lightning is not just a natural curiosity, but an integral part of their cultural identity and economic life. Local communities have developed sophisticated strategies for living with continuous lightning activity. Traditional architecture in the region incorporates lightning protection features that predate modern electrical engineering by centuries. Houses are often built with steep metal roofs that serve as natural lightning rods, directing electrical strikes safely to the ground. Traditional building techniques emphasize the use of non-conductive materials and include design features that minimize electromagnetic interference during electrical storms. The fishing industry, which employs thousands of people on Lake Maracaibo, has adapted to the electrical environment in fascinating ways. Experienced fishermen have developed an intuitive understanding of lightning patterns that allows them to predict not just when storms will occur, but where they will be most intense. This knowledge helps them position their boats and nets for optimal safety and productivity. Local fishing boats often incorporate specialized equipment designed to function in high electrical activity environments. Traditional wooden boats are preferred over modern fiberglass vessels because wood provides better electrical insulation. Many boats carry primitive but effective lightning protection systems, including copper chains that drag in the water to provide a conductive path for electrical discharge. The phenomenon has also created unique economic opportunities. Tourism related to the Catatumbo lightning generates millions of dollars annually for the regional economy. Visitors come from around the world to witness what tour operators call nature's greatest light show, creating jobs for guides, boat operators, hotel staff, and restaurant workers. Local artisans have developed a thriving craft industry based on lightning-related themes. Traditional weavers incorporate lightning-inspired patterns into textiles, while woodworkers carve lightning motifs into furniture and decorative objects. These crafts have found international markets among collectors of folk art and natural history enthusiasts. The lightning has also influenced regional cuisine in unexpected ways. Traditional cooking methods in the area include techniques specifically adapted to frequent electrical storms. Many families maintain wood-fired cooking facilities as backup systems for use during periods of intense electrical activity when electric power may be unreliable. Local medical practitioners have developed traditional knowledge about lightning-related health effects. While direct lightning strikes are relatively rare due to the predominantly intra-cloud nature of most discharges, the region's healthcare providers maintain expertise in treating electrical injuries and have developed protocols for managing the psychological effects of living in a high electrical activity environment. The phenomenon has inspired a rich tradition of music, literature, and visual arts. Regional musicians have composed traditional songs that incorporate the rhythm of thunder and the visual imagery of lightning. The Joropo Catatumbero is a traditional dance that mimics the flickering patterns of electrical discharge, while local poets have created extensive bodies of literature celebrating the lightning as a symbol of natural power and regional identity. Educational institutions in the region have developed specialized curricula that incorporate the lightning phenomenon into science education. Local schools often serve as informal research stations, with students participating in citizen science projects that contribute to ongoing scientific research. This has created a population with unusually sophisticated understanding of atmospheric science and electrical phenomena. Despite its status as a natural wonder, the Catatumbo lightning phenomenon faces significant environmental challenges that threaten its long-term survival. Understanding these threats is crucial for developing conservation strategies to protect this unique natural heritage. Changes in regional precipitation patterns could also affect the phenomenon. The lightning's intensity correlates with lake water levels and the surrounding wetland ecosystem's health. Prolonged droughts could reduce the moisture available for evaporation, while excessive flooding could disrupt the delicate balance of the river delta ecosystem. Human development around Lake Maracaibo poses direct threats to the environmental conditions that support the lightning phenomenon. Urban expansion, industrial development, and agricultural intensification have altered local microclimates and reduced the area of wetlands that contribute moisture to the atmosphere. The oil industry has a particularly significant presence in the Lake Maracaibo region. Venezuela's oil reserves are concentrated around the lake, and decades of petroleum extraction have resulted in environmental degradation that may affect the lightning phenomenon. Oil spills and industrial pollution have contaminated water and soil, potentially altering the chemical composition of atmospheric moisture. Deforestation in the surrounding mountains disrupts the atmospheric circulation patterns that help drive the lightning phenomenon. Forest clearing changes local albedo, reflectivity patterns, alters evapotranspiration rates, and disrupts the mountain-valley wind systems that are crucial for storm formation. Agricultural development has converted much of the natural wetland habitat around the lake to pasture and cropland. These changes reduce the area available for natural evaporation and transpiration, while altering surface heating patterns that contribute to atmospheric instability. Water management practices, including dam construction and river diversions, have altered the natural flow patterns of the Catatumbo River and other waterways feeding into Lake Maracaibo. These changes affect the distribution of freshwater input and may disrupt the salinity gradients that influence evaporation patterns. The introduction of invasive species to the Lake Maracaibo ecosystem has disrupted natural ecological relationships that may indirectly affect the lightning phenomenon. Invasive aquatic plants can alter water temperature patterns and evaporation rates, while invasive fish species can disrupt food webs in ways that affect the health of wetland ecosystems. Perhaps most concerning is the potential for cumulative effects. The combination of multiple environmental stressors could push the system past a tipping point where the unique conditions necessary for the Catatumbo lightning can no longer be maintained. The Catatumbo lightning phenomenon represents far more than just an impressive natural spectacle. It serves as a crucial natural laboratory for advancing our understanding of atmospheric electricity, climate dynamics, and extreme weather phenomena. The insights gained from studying this unique system have applications ranging from improved weather forecasting to aviation safety. Research at Lake Maracaibo has contributed fundamental knowledge about lightning formation processes that applies globally. The extreme consistency and intensity of the electrical activity allows scientists to study phenomena that occur too rarely in other locations to permit systematic investigation. This includes detailed analysis of lightning channel formation, charge distribution within storm clouds, and the relationship between atmospheric conditions and electrical discharge patterns. The phenomenon serves as a natural testing ground for lightning detection and measurement technologies. Instruments developed and calibrated at Catatumbo are used worldwide for lightning research and operational weather monitoring. The intense electrical activity provides an ideal environment for testing the limits of detection equipment and developing new measurement techniques. Because the phenomenon is so sensitive to atmospheric conditions, changes in its behavior can help scientists. Scientists are developing lightning fingerprints that could provide early warning of shifts in tropical regions. Future research directions include increasingly sophisticated computer modeling of the entire Lake Maracaibo atmospheric system. Scientists are working to develop predictive models that can forecast lightning activity days or even weeks in advance, which would have significant benefits for aviation safety, agriculture, and tourism planning. Space-based research is expanding with new satellite missions designed specifically to study lightning from orbit. These missions will provide unprecedented detail about the Catatumbo phenomenon, while also enabling comparison with other high lightning activity regions around the world. One particularly exciting area of investigation involves the potential relationship between lightning activity and seismic processes. Some researchers hypothesize that the geological stress patterns around Lake Maracaibo, which sits in a seismically active region, may influence atmospheric electrical activity through mechanisms that are not yet fully understood. Advances in artificial intelligence and machine learning are being applied to lightning research, with algorithms designed to identify patterns in electrical activity that might not be apparent through traditional statistical analysis. These techniques may reveal new insights about the complex relationships between atmospheric conditions and lightning formation. International collaboration is expanding as researchers from around the world recognize the global significance of Catatumbo lightning research. Joint projects involve institutions from multiple countries and continents, bringing together expertise in atmospheric physics, climate science, and electrical engineering. The phenomenon is also contributing to our understanding of atmospheric electricity on other planets. Scientists studying the atmospheres of Jupiter, Saturn, and Venus use knowledge gained from Catatumbo research to interpret observations of electrical activity in alien atmospheres. The Venezuelan government has recognized the phenomenon's importance by proposing its designation as a UNESCO World Heritage Site. This designation would provide international recognition and potentially access to conservation funding, while also raising global awareness about the need to protect the unique environmental conditions that support the lightning. Local conservation efforts focus on protecting and restoring the wetland ecosystems that are crucial for maintaining the atmospheric conditions necessary for lightning formation. This includes reforestation projects in the surrounding mountains, restoration of degraded wetlands, and implementation of sustainable agricultural practices that minimize environmental impact. Community-based conservation programs engage local residents as active participants in protection efforts. These programs recognize that the people who live around Lake Maracaibo have the greatest stake in preserving the phenomenon that is so central to their cultural identity and economic well-being. Educational initiatives are crucial for building understanding and support for conservation efforts. Programs targeting schools, community groups, and tourism operators help create a constituency committed to protecting the lightning phenomenon for future generations. Research-based conservation involves ongoing scientific monitoring to detect early signs of environmental degradation that could threaten the phenomenon. This includes regular measurements of water quality, atmospheric chemistry, and ecosystem health indicators. International cooperation is essential given that atmospheric phenomena don't respect political boundaries. Research partnerships with institutions in other countries provide access to expertise and resources while also contributing to global understanding of atmospheric electricity. Policy initiatives focus on regulating development and industrial activities that could harm the environmental conditions supporting the lightning phenomenon. This includes environmental impact assessments for proposed developments and enforcement of existing environmental protection laws. Economic incentives for conservation include programs that provide alternative livelihoods for communities that might otherwise rely on environmentally destructive activities. Ecotourism development, sustainable fisheries management, and support for traditional crafts provide economic alternatives that support both community well-being and environmental protection. While the Catatumbo lightning is unique in its intensity and consistency, understanding it in the context of other global lightning phenomena provides important insights into the atmospheric processes that create electrical storms worldwide. Several other locations around the world experience high levels of lightning activity, though none approach the intensity of Lake Maracaibo. Central Africa's Congo Basin experiences frequent lightning during its wet season, with some areas recording 100 to 150 strikes per square kilometer annually. The difference is that African lightning shows much more seasonal variation and lacks the remarkable consistency of the Catatumbo phenomenon. The southeastern United States, particularly Florida, experiences intense lightning activity during summer months, with some areas recording 80 to 100 strikes per square kilometer annually. However, this activity is highly seasonal and weather-dependent, lacking the predictable nightly occurrence that characterizes Catatumbo. The Himalayan region experiences unique lightning patterns related to monsoon circulation and high-altitude atmospheric dynamics. While not as frequent as Catatumbo, Himalayan lightning provides insights into how extreme topography influences atmospheric electrical processes. Comparative studies reveal that the Catatumbo phenomenon's uniqueness lies not just in its intensity, but in the specific combination of factors that create such consistent conditions. Most other high lightning regions depend on seasonal weather patterns or specific meteorological events, while Catatumbo's activity is sustained by permanent geographical features. Research comparing different lightning hotspots has contributed to our understanding of what atmospheric scientists call lightning climatology, the study of how lightning patterns relate to regional climate and geography. This field has important applications for weather prediction, modeling, and understanding how lightning patterns. The global perspective on lightning research has revealed that atmospheric electrical activity plays important roles in Earth's climate system that extend far beyond local weather effects. Lightning contributes to the global electrical circuit, influences atmospheric chemistry on a planetary scale, and affects the distribution of nitrogen compounds throughout the Earth system. Conclusion: the eternal dance of fire and sky. As we reach the end of our journey through the spectacular world of Catatumbo lightning, it's worth reflecting on what this phenomenon teaches us about the incredible complexity and beauty of our planet's atmospheric system. Here, in this remote corner of Venezuela, nature has created something truly extraordinary, a place where the fundamental forces of physics create a light show that has dazzled observers for centuries. The Catatumbo lightning represents the perfect convergence of geography, weather, and atmospheric physics. It reminds us that our planet is still capable of surprises, still harboring natural phenomena that challenge our understanding and inspire our sense of wonder. In an age when we sometimes feel that every corner of the Earth has been mapped and measured, the lightning over Lake Maracaibo continues to reveal new secrets to scientists willing to study its mysteries. But perhaps more importantly, the phenomenon serves as a powerful reminder of how delicately balanced our natural systems truly are. The specific combination of factors that creates this lightning, the lake's thermal properties, the surrounding topography, the regional weather patterns, the ecosystem relationships, all work together in precise harmony. Disrupting any one component could potentially affect the entire system. This makes the Catatumbo lightning not just a natural wonder to be admired, but a natural treasure to be protected. The communities around Lake Maracaibo have lived with this phenomenon for generations, adapting their lives and cultures to its rhythms. They understand intuitively what science has taken decades to demonstrate, that the lightning is not separate from the ecosystem, but an integral part of a complex natural system. The research conducted at Lake Maracaibo continues to advance our understanding of atmospheric electricity, contributing to improved weather forecasting, better aviation safety protocols, and deeper insights into how extreme weather systems function. Every lightning strike over the lake adds to our global knowledge base, helping scientists around the world better understand and predict atmospheric electrical phenomena. The phenomenon also serves as a bridge between scientific inquiry and cultural heritage. The indigenous peoples of the region understood the lightning's patterns long before scientists arrived with their instruments and theories. Their traditional knowledge, passed down through generations, complements modern research and reminds us that scientific understanding benefits from multiple ways of knowing and observing the natural world. For those of us fortunate enough to study atmospheric sciences, the Catatumbo lightning represents the ultimate field laboratory, a place where theory meets reality in the most spectacular fashion imaginable. It challenges our models, tests our instruments, and continually surprises us with new phenomena to investigate and understand. The tourism that the lightning generates brings economic benefits to local communities, while also creating a constituency of people from around the world who have witnessed this natural wonder firsthand. These visitors return to their home countries as ambassadors for conservation, carrying with them not just photographs and memories, but a deeper appreciation for the importance of protecting our planet's most extraordinary natural phenomena. In our increasingly urbanized world, where artificial lights often obscure the night sky and technology mediates much of our experience with nature, the Catatumbo lightning offers something increasingly rare: a direct, unfiltered encounter with the raw power and beauty of natural forces. Standing on the shore of Lake Maracaibo on a stormy night, watching the sky explode with electrical fire is to experience something that connects us directly to the fundamental forces that shape our planet. The lightning also serves as a powerful metaphor for the interconnectedness of natural systems. What appears to be a local phenomenon is actually the product of global weather patterns, regional geography, local ecosystems, and atmospheric chemistry working together in complex ways. The lightning reminds us that in nature, everything is connected, that changes in one part of the system can have effects that ripple out in unexpected ways. As we continue to study and work to protect the Catatumbo lightning, we're not just preserving a spectacular natural phenomenon, we're protecting a natural laboratory that helps us understand our planet's atmospheric systems, a cultural heritage site that has shaped human communities for centuries, and a source of wonder and inspiration for people around the world. Final thoughts. Lessons from the lightning. The study of Catatumbo lightning teaches us several important lessons that extend well beyond atmospheric physics. First, it demonstrates the value of long-term observation and indigenous knowledge. The phenomenon was known and understood by local communities for centuries before it became the subject of formal scientific study. This reminds us that traditional ecological knowledge often provides crucial insights that complement and inform scientific research. Second, the phenomenon illustrates the importance of thinking systemically about environmental problems. The lightning cannot be understood or protected by focusing solely on atmospheric processes. It requires understanding the entire ecosystem, from the lake's thermal dynamics to the mountain forests, to the wetland vegetation that contributes moisture to the atmosphere. Third, the research at Catatumbo shows how local phenomena can have global significance. The insights gained from studying this unique lightning system contribute to our understanding of atmospheric electricity worldwide, with applications for weather prediction, aviation safety, and climate research that benefit people far from Lake Maracaibo. Fourth, the conservation challenges facing the phenomenon highlight the complex relationships between human development, environmental protection, and cultural preservation. Protecting the lightning requires balancing the economic needs of local communities with the environmental conditions necessary to sustain this natural wonder. Finally, the Catatumbo lightning reminds us of the importance of maintaining our sense of wonder about the natural world. In our scientific age, it's easy to reduce natural phenomena to equations and measurements, but the lightning over Lake Maracaibo is more than the sum of its meteorological parts. It's a source of beauty, inspiration, and cultural meaning that enriches human experience in ways that cannot be quantified. As we face an uncertain environmental future, phenomena like the Catatumbo lightning serve as both inspiration and motivation. They show us what our planet is capable of creating when conditions are right, and they remind us of our responsibility to protect the natural systems that make such wonders possible. The next time you see lightning flash across the sky during a thunderstorm, remember the eternal lightning of Lake Maracaibo, a place where nature puts on a nightly show that has been running continuously for centuries, where the sky catches fire nearly 300 nights a year, and where the marriage of geography, climate, and physics creates one of the most spectacular natural phenomena on Earth. In closing, let me return to where we began, with numbers that tell only part of the story. Yes, Lake Maracaibo experiences 250 lightning strikes per square kilometer per year. Yes, the phenomenon occurs on 297 nights annually. Yes, peak activity can produce 300 flashes per minute. But beyond the statistics lies something more profound, a reminder that our planet is still capable of wonder, still hiding secrets in remote corners, still creating phenomena that humble our understanding and inspire our sense of awe. The Catatumbo lightning stands as testament to the power and beauty of natural forces, a bridge between scientific inquiry and cultural heritage, and a call to action for environmental protection. It is, in the words of one indigenous elder, the place where the sky remembers how to dance. And what a dance it is, eternal, magnificent, and irreplaceable. May it continue to light up the Venezuelan sky for generations to come, reminding us all that in nature, the impossible is simply waiting for the right conditions to become inevitable. Thank you for joining me on this electrifying journey through one of our planet's most extraordinary natural phenomena. Class dismissed. But the lightning, as always, continues. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you. Tonight we're going to learn about forgotten American theme parks. So, as you settle in, please take a moment to let us know where you're listening from and feel free to subscribe. Now, as we begin, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. Okay, let's begin our exploration of forgotten American theme parks, dreams deferred and rust-covered fantasies, the rise and fall of America's lost entertainment empires. Before we dive into today's topic, let me ask you a question. How many of you have been to Disney World or Disneyland? Right, most of you. Now, how many of you have heard of Freedomland, USA? What about Riverview Park in Chicago? Action Park in New Jersey? Tonight, we're going to explore the fascinating and often tragic world of America's forgotten theme parks. Those ambitious dreams that promised magic but delivered bankruptcy, those grand visions that became overgrown lots, and yes, those death traps that somehow operated for decades. We'll examine why these parks failed when others succeeded, what they tell us about American culture and economics, and why some of them have achieved almost mythical status in the decades since their closure. But first, let me warn you. By the end of this lecture, you may find yourself spending your weekend going down Wikipedia rabbit holes about abandoned roller coasters and defunct water parks. Don't say I didn't warn you. The Golden Age and its shadows. To understand forgotten theme parks, we must first understand the context in which they emerged. The post-World War II boom created a perfect storm for entertainment ventures. Americans had disposable income, leisure time was increasing, and the automobile made previously inaccessible locations suddenly viable for large-scale entertainment complexes. Disneyland opened in 1955, fundamentally changing what Americans expected from amusement parks. Walt Disney didn't just create a collection of rides, he created an immersive experience, a carefully crafted fantasy world. The success of Disneyland spawned dozens of imitators, each hoping to capture lightning in a bottle. Most would fail spectacularly. The difference between Disney's success and others' failures often came down to three critical factors: vision, execution, and financial backing. Disney had all three. Many of our forgotten parks had grand visions but lacked the execution or the deep pockets necessary to realize them properly. Case Study 1, Freedomland, USA, 1960 to 1964. The park that thought it was America. Let's start with perhaps the most ambitious failure in theme park history. Freedomland, USA, in the Bronx, New York. Opened in 1960, Freedomland was designed to be nothing less than a miniature version of the entire United States. The park was literally shaped like the continental U.S., with different regions representing different parts of the country. Visitors could travel from the Great Plains section to New England via stagecoach, riverboat, or railroad. The park featured elaborate historical recreations, including a Chicago fire show where an entire building would burn down multiple times daily, which in retrospect seems like an expensive way to entertain people, but this was the era of bigger is better. The park's tagline was, "The world's largest entertainment center," and at 205 acres, it was indeed massive. The opening day drew 69,000 visitors, and initial projections suggested Freedomland would attract 4 million visitors annually. These projections proved wildly optimistic. What went wrong? Several factors contributed to Freedomland's rapid demise. First, the location. While the Bronx seemed logical, close to Manhattan's population center, it was actually difficult to reach by car, and public transportation connections were poor. Disney had learned this lesson when choosing Anaheim over locations closer to Los Angeles proper. Second, the concept, while ambitious, was confused. Was it an educational experience about American history? A thrill park? A cultural attraction? The park never quite figured out its identity, trying to be everything to everyone and succeeding at being nothing to anyone. Third, and perhaps most critically, the park was undercapitalized from the beginning. The elaborate shows and attractions were expensive to maintain, but ticket prices couldn't be raised high enough to cover costs without alienating the middle-class families the park needed to survive. The Chicago Fire Show alone required a full-time crew and massive amounts of lumber and other materials that literally went up in smoke 8 times a day. Weather was another issue. Unlike Disneyland's year-round California climate, Freedomland had to deal with harsh New York winters. The park was only profitable during summer months, but fixed costs continued year-round. By 1964, after burning through millions of dollars, Freedomland closed permanently. The site eventually became a shopping center, because nothing says American dream deferred, like a strip mall built on the ruins of a theme park shaped like America. The lesson of Freedomland? Vision without viable economics is just an expensive fantasy. Walt Disney understood this. His successors often didn't. Case Study 2. Action Park, 1978 to 1996. The most dangerous amusement park in America. Now let's shift from noble failure to spectacular negligence with Action Park in Vernon Township, New Jersey. Action Park earned the nickname Traction Park due to the frequency of injuries, and Class Action Park due to the lawsuits. It was a water park that seemed designed by someone who had heard the concept of safety regulations, but decided they were more like suggestions. Action Park was the brainchild of Eugene Mulvihill, a man who apparently believed that the best way to ensure fun was to remove all obstacles to it, including common sense, proper engineering, and basic safety protocols. The park featured attractions that would make modern insurance adjusters weep. Consider the Cannonball Loop, a water slide with an actual loop-de-loop. The slide was tested with crash test dummies, which came out of the loop dismembered. When this was reported to management, their response was essentially, well, the dummies aren't human, so probably it's fine. The slide operated for about a month in 1985 before being permanently closed. Rumors persist that it occasionally opened for employees on especially hot days, but officially, it remained shuttered. Then there was the Alpine Slide, a concrete track down a mountain where riders controlled their speed via handbrakes. The problem? The brakes often didn't work, and the concrete track could reach temperatures of 190 degrees Fahrenheit in summer. Riders regularly suffered severe abrasions, Action Park tattoos, when they crashed or were thrown from their sleds. The park's solution was to post signs warning riders to keep their speed down, as if teenagers on vacation were known for their cautious decision-making. The Tarzan swing was another marvel of engineering negligence. Riders would swing from a 20-foot rope into a pool of water. Simple enough, except the water was spring-fed and therefore extremely cold, often around 50 to 60 degrees Fahrenheit. The shock of hitting the frigid water caused many visitors to go into shock and begin drowning. The park employed several lifeguards specifically for this one attraction, and they were among the busiest employees in the park. But perhaps the most notorious attraction was the kayak experience, where visitors would navigate real whitewater rapids in individual kayaks. The rapids were fed by snowmelt and were genuinely dangerous. Visitors regularly became trapped under rocks or in hydraulics. The park employed professional kayakers as lifeguards, but even they couldn't prevent all accidents. Between 1978 and 1996, Action Park was associated with at least 6 deaths and countless injuries. The park faced numerous lawsuits, but somehow managed to stay open for nearly 2 decades. How? Partly because it was genuinely popular. Despite, or perhaps because of, its dangerous reputation, Action Park attracted visitors who wanted an authentic thrill experience. It was the anti-Disney, a place where real danger lurked behind every corner. The park also benefited from New Jersey's relatively lax regulation of amusement parks in the 1980s. Most oversight was left to local authorities, and Vernon Township apparently took a hands-off approach to regulating what was likely their largest employer and tax generator. Action Park finally closed in 1996 after mounting legal costs and insurance problems made it financially unviable. The site was later reopened as Mountain Creek, which operated much more conventional and much safer attractions. Action Park's legacy is complex. On one hand, it represents everything wrong with unregulated capitalism applied to entertainment, a place where profit clearly took precedence over public safety. On the other hand, it has achieved cult status among Generation X visitors who remember it fondly as a place where they experienced genuine thrills and real freedom, however dangerous. The documentary Class Action Park captures this paradox perfectly, featuring interviews with former visitors who describe horrifying accidents in the same breath as they express nostalgia for the experience. It's a uniquely American phenomenon, nostalgic affection for a place that tried to kill you. Case Study 3, Riverview Park, Chicago 1904 to 1967, The Lost Crown Jewel. Not all forgotten theme parks were failures in the traditional sense. Some were actually quite successful but fell victim to changing economics, urban development pressures, or simple bad timing. Riverview Park in Chicago is perhaps the best example of a beloved park that died not from failure, but from success in the wrong place at the wrong time. Riverview opened in 1904 on the north side of Chicago and quickly became one of America's premier amusement parks. The park was famous for its roller coasters, particularly the Bobs, which was considered one of the finest wooden coasters ever built. The park also featured the parachute jump, the rotor, and countless other attractions that defined the American amusement park experience for generations of Chicagoans. At its peak, Riverview attracted over 2 million visitors annually and employed over 1,000 people during the summer season. The park was particularly famous for its Halloween celebrations and its role in Chicago's social life. For many Chicagoans, particularly working-class families, Riverview was their primary source of affordable entertainment. So why did such a successful park close? The answer lies in the complex economics of urban land use in the 1960s. By the mid-1960s, the land Riverview occupied had become extremely valuable for residential development. The park covered 74 acres in a rapidly gentrifying neighborhood, and the property taxes alone were becoming prohibitive. More importantly, the park's seasonal nature made it a poor economic use of such valuable land. For 9 months of the year, those 74 acres sat largely empty, generating minimal revenue while property taxes continued to mount. Meanwhile, developers were offering enormous sums for the land, knowing they could build apartment complexes and shopping centers that would generate revenue year-round. The park's owners, the Schmidt family, faced a difficult decision. They could invest millions in modernizing the park and hope to compete with newer suburban attractions like Great America, or they could sell the land for development and retire wealthy. They chose the latter, announcing in 1967 that Riverview would close permanently at the end of the season. The final day of operation, October 3, 1967, drew enormous crowds. Many visitors took pieces of the park as souvenirs. Fragments of rides, signs, anything they could carry. The Chicago Tribune reported that grown men wept as the Bobs was demolished. Riverview's closure marked the end of an era in American entertainment. It was one of the last great urban amusement parks, a place integrated into the city's fabric rather than isolated in suburban sprawl. Its loss was mourned not just by Chicagoans, but by amusement park enthusiasts nationwide who recognized that something irreplaceable had been lost. The site is now occupied by DeWitt University and a shopping center. A small plaque marks the approximate location of the park's entrance, but otherwise, no trace remains of what was once one of America's great entertainment destinations. Riverview's story illustrates a crucial point about forgotten theme parks. Sometimes they die not because they failed, but because they succeeded too well in places that became too valuable for entertainment. It's a particularly American tragedy, the sacrifice of communal joy on the altar of economic efficiency. The economics of failure. Why theme parks die. Before we continue with more case studies, let's pause to examine the common factors that lead to theme park failure. Understanding these patterns helps us appreciate why places like Disney World succeed while others become overgrown ruins. Location, location, location. Many failed parks chose locations that seemed logical but proved problematic. Freedomland was close to New York City but hard to reach. Others were built in areas with seasonal climates that limited operating periods, or in regions without sufficient population density to support year-round operation. Undercapitalization. Theme parks require enormous upfront investments and substantial ongoing maintenance costs. Many failed parks opened with insufficient capital reserves, leaving them unable to properly maintain attractions or weather inevitable rough patches. Identity crisis. Successful theme parks know what they are. Disney parks are immersive fantasy experiences. Six Flags parks are thrill ride destinations. Many failed parks tried to be everything: educational and thrilling, local and universal, nostalgic and cutting edge, and ended up being nothing coherent. Competition. The theme park industry is brutally competitive. Disney's success spawned dozens of imitators, but the market could only support so many large-scale operations. Many parks failed not because they were poorly run, but because they were late to market or couldn't differentiate themselves sufficiently. Changing demographics. Some parks that thrived for decades found themselves obsolete as their customer base aged, moved away, or developed different entertainment preferences. The rise of video games, home entertainment systems, and other leisure options has made it harder for traditional parks to compete for attention. Insurance and liability. As safety regulations tightened and liability insurance costs increased, some parks found they couldn't afford to operate safely. Action Park represents an extreme case, but many smaller parks simply couldn't afford the insurance premiums required to stay open. Real estate values. Like Riverview, some successful parks became victims of their own valuable real estate. As urban areas gentrified or suburban land became more valuable for other uses, the economic pressure to sell became irresistible. Case Study 4. Conneaut Lake Park, 1892 to 2019. The slow death of a century. Sometimes theme park death is not a sudden closure but a slow decline spanning decades. Conneaut Lake Park in Pennsylvania represents this type of forgotten park, one that struggled for years to maintain relevance and financial viability before finally succumbing to economic reality. Founded in 1892, Conneaut Lake Park was one of America's oldest continuously operating amusement parks. Located in northwestern Pennsylvania, along the shores of Conneaut Lake, the park was originally a trolley park, a destination built by trolley companies to generate weekend ridership on their systems. The park's centerpiece was the Blue Streak, a wooden roller coaster built in 1938 that was considered one of the finest coasters of its era. The park also featured a historic hotel, a beach, boat rentals, and various other attractions that made it a popular summer destination for families throughout the region. For most of its history, Conneaut Lake Park operated successfully as a regional attraction. It never aspired to compete with Disney World or other megaparks, instead focusing on providing affordable family entertainment for visitors from Ohio, Pennsylvania, and Western New York. The park's problems began in the 1980s as competition increased and operating costs rose. Newer parks with modern attractions and better financing drew visitors away. The park's infrastructure, much of it built in the early 20th century, required constant, expensive maintenance. The seasonal nature of the business, the park was only profitable during summer months, made it difficult to generate sufficient revenue to cover year-round expenses. The park changed hands several times, with each new owner promising to restore it to former glory. Some improvements were made, but the fundamental economic challenges remained. The park's location, which had been an asset when most Americans vacationed close to home, became a liability in an era when families were willing to travel across the country to visit world-class attractions. Conneaut Lake Park's final years were marked by sporadic closures, bankruptcy filings, and desperate attempts to find new sources of revenue. The park briefly tried operating as a concert venue, hosted festivals, and even attempted to market itself as a filming location for period movies. The Blue Streak, the park's most famous attraction, became a symbol of the park's struggles. By the 2000s, the coaster required expensive repairs that the park couldn't afford. It operated intermittently, sometimes closing mid-season when problems developed. Enthusiasts organized fundraising campaigns to help maintain the historic coaster, but these efforts could only delay the inevitable. The park officially closed in 2019, though it had been operating only sporadically for several years. The Blue Streak was dismantled and sold, ending more than 80 years of operation. The park's other buildings and attractions were either demolished or left to decay. Conneaut Lake Park's story represents the fate of many smaller regional parks that couldn't adapt to the changing entertainment landscape. These parks often had loyal local followings and significant historical value, but they lacked the resources to modernize and compete with better-funded attractions. The park's decline also illustrates the challenges facing seasonal businesses in areas with declining populations. Northwestern Pennsylvania, like many Rust Belt regions, has seen its population decrease steadily for decades. The young families that had been the park's core customer base simply weren't there anymore, and those who remained often preferred to spend their entertainment dollars on trips to larger, more modern attractions. Case Study 5. Geauga Lake, 1887 to 2007. When corporate giants collide, our final major case study involves a park that survived for 120 years before becoming collateral damage in the corporate wars between theme park giants. Geauga Lake in Aurora, Ohio demonstrates how even successful parks can be destroyed when they become pawns in larger business strategies. Geauga Lake began as a picnic grove in 1887 and gradually evolved into a full-scale amusement park. For most of its history, it operated as a modest regional attraction, serving families from Cleveland, Akron, and surrounding areas. The park featured a mix of classic attractions including wooden roller coasters, a traditional midway, and water rides. The park's transformation and ultimate destruction began in 2000 when Premier Parks, later Six Flags, purchased the facility and embarked on an ambitious expansion program. Six Flags invested over $40 million in new attractions, including several large steel roller coasters that transformed the modest regional park into a major thrill destination. The expansion was part of Six Flags' strategy to compete with Cedar Point, located about 90 minutes away. Cedar Point was and remains one of America's premier roller coaster parks, and Six Flags apparently believed they could create a competing mega park at Geauga Lake. In 2001, Six Flags made an even bolder move, purchasing the adjacent SeaWorld Ohio and combining the two properties into a single, massive complex. The combined park, marketed as Six Flags Worlds of Adventure, covered over 700 acres and featured both traditional amusement park attractions and marine life shows. The concept seemed logical on paper: create a park that combined the thrill rides of Six Flags with the family-friendly marine shows of SeaWorld, offering something for every visitor. In practice, the combination was problematic. The two parks had different operational philosophies and customer bases. SeaWorld visitors expected educational, family-oriented experiences, while Six Flags customers wanted high-intensity thrill rides. More importantly, the combined operation was extremely expensive to maintain. The marine life required specialized care and facilities, while the thrill rides needed constant maintenance and safety inspections. The park struggled to generate sufficient revenue to cover these costs, while keeping ticket prices competitive. After just a few years, Six Flags began to have second thoughts about the Ohio venture. The company was facing financial difficulties nationwide and needed to shed unprofitable operations. In 2004, Six Flags sold Geauga Lake to Cedar Fair, the company that operated Cedar Point. Cedar Fair's purchase of Geauga Lake initially seemed like good news for the park. Cedar Fair had extensive experience operating successful parks, and their ownership of nearby Cedar Point suggested they understood the Ohio market. However, Cedar Fair's real motivation appears to have been eliminating competition rather than operating two parks. Almost immediately after purchasing Geauga Lake, Cedar Fair began scaling back operations. The marine life shows were eliminated. Several roller coasters were removed and relocated to other Cedar Fair parks, and marketing support was reduced. The company claimed they were right-sizing the park, but it became clear that Cedar Fair saw Geauga Lake primarily as a competitor to be neutralized rather than an asset to be developed. By 2007, Cedar Fair announced that Geauga Lake would close permanently. The company claimed the park was unprofitable, but critics argued that Cedar Fair had deliberately run the park into the ground to eliminate competition for Cedar Point. Supporting this theory was the fact that several of Geauga Lake's attractions were quickly moved to other Cedar Fair properties, suggesting they were valuable assets that could have continued operating profitably at Geauga Lake. The closure of Geauga Lake was particularly painful for enthusiasts because the park had been successfully operating for over a century before corporate machinations led to its demise. Unlike parks that failed due to poor location, inadequate financing, or lack of customer interest, Geauga Lake died because it became inconvenient for a corporate parent more interested in protecting market share than preserving history. The former Geauga Lake site now houses a Walmart and other retail development. The only remnant of the park is a small portion of the property that continues to operate as a water park, a pale shadow of what was once one of Ohio's premier entertainment destinations. The afterlife of forgotten parks, urban exploring, and nostalgic tourism. What happens to theme parks after they die? The answer varies depending on the value of the underlying real estate and the completeness of the closure process. Some, like Freedomland and Riverview, are completely redeveloped, leaving no trace of their former existence. Others become ruins that attract urban explorers, photographers, and nostalgic visitors. Perhaps the most famous example of theme park ruins is the abandoned sections of Six Flags New Orleans, which closed permanently after Hurricane Katrina in 2005. The flooded park was never repaired or cleaned up, leaving a surreal landscape of rusting roller coasters and decaying buildings slowly being reclaimed by nature. The site has become a popular destination for urban explorers and has been used as a filming location for several movies and television shows. These abandoned parks have developed their own subculture of enthusiasts who document the ruins, research the history, and sometimes organize informal gatherings at the sites. Websites like darkride.com and abandonedbutnotforgotten.com serve as repositories for photos, memories, and historical information about defunct parks. The psychology of this interest in abandoned theme parks is fascinating. These places were designed to create joy and wonder, so their abandonment carries particular poignancy. There's something deeply unsettling about seeing a carousel slowly rusting in an overgrown field, or walking through the remains of a funhouse where children once laughed and screamed. Some entrepreneurs have attempted to capitalize on this interest by developing ruin tourism attractions. The most successful example is probably the abandoned city of Pripyat near Chernobyl, which includes an amusement park that was never opened due to the nuclear accident. Tours of Pripyat regularly include stops at the unused Ferris wheel and bumper car pavilion, which have become iconic symbols of interrupted dreams. Lessons for the present. What dead parks teach us about live ones. The study of forgotten theme parks offers valuable insights into the current industry and broader patterns in American entertainment and culture. Several key lessons emerge from examining these failures. Sustainability trumps spectacle. The most common cause of park failure is not lack of ambition, but lack of sustainable business models. Parks that focused on creating sustainable operations, reasonable operating costs, appropriate scale for their markets, reliable revenue streams, tended to survive longer than those that prioritized spectacular attractions without considering long-term viability. Location remains crucial. Despite advances in transportation and marketing, location continues to be the most important factor in theme park success. Parks need to be accessible to sufficient populations and situated in areas that support year-round or at least extended season operation. Corporate consolidation has costs. The consolidation of the theme park industry into a few major operators has led to greater efficiency and higher safety standards. But it has also resulted in less diversity and the closure of parks that might have remained viable under different ownership structures. Cultural values change. Many forgotten parks reflected the cultural values and assumptions of their eras in ways that became problematic over time. Freedomland's celebration of American history ignored uncomfortable realities about colonization and slavery. Action Park's libertarian approach to safety reflected 1980s attitudes that seem reckless today. Technology disruption is constant. The rise of television, video games, home entertainment systems, and digital media has continuously challenged theme parks to justify their relevance. Parks that failed to adapt to changing entertainment preferences often found themselves serving shrinking markets. Community connection matters. Parks with strong connections to their local communities, places that served as gathering spots for generations of families, tended to inspire more loyalty and support than those that positioned themselves purely as tourist destinations. The future of forgetting. Which parks might be next? As we look to the future, several trends suggest which currently operating parks might be at risk of joining our list of forgotten attractions. Climate change poses challenges for parks in areas prone to extreme weather. Rising insurance costs and safety regulations make it increasingly difficult for smaller operators to compete. Changing demographics and entertainment preferences continue to erode the customer base for traditional amusement parks. Several specific parks appear vulnerable. Many smaller regional parks, particularly those in areas with declining populations, face ongoing financial pressures. Some larger parks that were built during the expansion boom of the 1990s and 2000s may find themselves overbuilt for their markets as competition increases. The COVID-19 pandemic has accelerated many of these trends, forcing several parks into bankruptcy or closure. While the largest operators like Disney and Universal have the resources to weather temporary setbacks, smaller and regional parks may not survive extended periods of reduced attendance. However, the pandemic has also demonstrated the continuing appeal of theme parks as shared experiences that cannot be replicated digitally. Despite all the technological disruption of recent decades, people still crave the physical thrills and social experiences that only theme parks can provide. Preservation efforts, saving what remains. The loss of so many historic theme parks has inspired various preservation efforts. Organizations like the National Amusement Park Historical Association work to document and preserve the history of defunct parks. The American Coaster Enthusiasts Organization campaigns to save historically significant roller coasters and other attractions. Some preservation efforts have been successful. When Astroland in Coney Island closed in 2008, preservationists managed to save the historic Cyclone roller coaster, which continues to operate under new management. The carousel from the defunct Glen Echo Park in Maryland was restored and relocated to a new facility where it continues to operate. Museums like the Strong National Museum of Play in Rochester, New York, house collections of artifacts from defunct parks, preserving everything from vintage ride vehicles to promotional materials. These collections ensure that future researchers and enthusiasts will have access to the physical remnants of America's forgotten entertainment history. Digital preservation efforts are also underway. Websites, databases, and social media groups dedicated to defunct parks preserve thousands of photos, videos, and personal memories that might otherwise be lost. YouTube channels like Expedition Theme Park and Defunctland produce high-quality documentaries about closed parks, introducing new generations to these forgotten places. Cultural impact: how forgotten parks live on. Despite their physical disappearance, many forgotten theme parks continue to influence American culture in subtle ways. Action Park inspired numerous comedy sketches, documentaries, and even a feature film. The park's reputation for danger has become a shorthand for reckless 1980s excess, referenced in everything from television shows to academic papers about risk management. Freedomland's influence can be seen in various subsequent attempts to create historically themed entertainment, from colonial Williamsburg's modern incarnation to the various historically themed areas in current Disney parks. The park's failure taught the industry valuable lessons about the importance of coherent storytelling and authentic detail in themed entertainment. Riverview Park lives on in the memories of Chicagoans and in the design philosophy of parks that prioritize community connection over tourist appeal. The park's integration into urban fabric serves as a model for modern attractions, trying to serve local populations rather than just tourists. Even unsuccessful parks contributed to the evolution of theme park design and operation. Each failure taught the industry valuable lessons about location, financing, safety, and customer service. In a very real sense, the forgotten parks helped build the successful parks we enjoy today. Conclusion: what we lose when we forget. As we reach the end of our journey through America's forgotten theme parks, it's worth reflecting on what we lose when these places disappear from both the landscape and collective memory. Theme parks are more than just collections of rides and attractions. They are repositories of dreams, gathering places for families and communities, and physical manifestations of our hopes for fun, excitement, and escape from everyday concerns. When Freedomland closed, America lost not just an entertainment venue, but a place that had tried, however imperfectly, to make history come alive for ordinary families. When Action Park shut down, we lost a place that, despite its dangers, had offered genuine thrills and authentic risks in an increasingly sanitized world. When Riverview was demolished, Chicago lost a community gathering place that had served generations of families. The study of forgotten theme parks reminds us that nothing lasts forever, that even our most cherished institutions are vulnerable to changing economics, demographics, and cultural values. It also reminds us of the importance of documenting and preserving the history of places that brought joy to millions of people, even if they ultimately failed as business enterprises. Perhaps most importantly, examining these forgotten parks helps us appreciate the ones that survive. Every successful theme park represents not just good business planning and execution, but also a victory over all the forces that destroyed their forgotten predecessors. When you visit Disney World or Cedar Point or any other surviving park, remember that you're experiencing something that dozens of other visionaries attempted but failed to sustain. The forgotten theme parks teach us that dreams are fragile things, requiring not just imagination and ambition, but also careful planning, adequate resources, and more than a little luck to survive. They remind us that behind every successful entertainment empire are dozens of failed attempts, each with its own stories of hope, excitement, disappointment, and loss. In the end, perhaps the most fitting memorial to America's forgotten theme parks is not a physical monument, but our continued fascination with them. As long as people research their histories, share memories of visiting them, and learn from their failures, these parks remain alive in some fashion. They become part of our collective story about dreams pursued, risks taken, and the eternal human desire to create places where, at least for a few hours, magic might be real. Class dismissed. But remember, next week we're discussing the history of failed shopping malls, so those of you who enjoyed today's topic should probably prepare for another deep dive into American dreams deferred. And please, resist the urge to plan weekend trips to abandoned theme park sites. I can't be responsible for trespassing charges, tetanus infections, or existential crises brought on by seeing a rusted tilt-a-whirl slowly being consumed by kudzu. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.